Alright, now we have entered a new subtopic called the centripetal force in circular motion. Okay, this is the first question. A 1,000-kilogram car traveling at a constant speed of 15 meters per second enters the circular curve of a flat road with radius 50 meters. Show by calculation whether the car can go round the curve safely when the road is dry and the coefficient of static friction mu s equal to 0.6, or when the road is wet with the coefficient of static friction mu s equal to 0.3. All right. What's information given? We have the mass. Here he gives us the mass. Constant speed. So we have the v. It's on the road. Radius. So you want to know whether it can go safely or not. If it is dry, wet, this give you the coefficient of mu s. Okay, so these are the informations. We have the mass, velocity, and the radius. Okay, so in chapter 6, just like chapter 4, we have to first draw the free body diagram to show all the forces acting on the object. So we must first draw the free body diagram. So as you can see here, this is actually the car on the road. It's making a turning, making a turning at the curve. So this is the center of the curve. Maybe this is a U-turn or what? Yeah. So this is the center of the curve. It's the car and on the road. Maybe we see the car from behind. Okay. So on the car, it has the weight downward, it has the normal force upward, perpendicular to the surface, and the friction is towards the center of the circle. Okay, why towards the center of the circle? Friction towards the center of the circle because you want to prevent the car from going out from the circle. Because it's making a turn. Yeah, making a turn. So the tendency of the car, the motion of the car is moving forward. Moving forward, going out from the circle. So friction try to keep it to oppose the motion, try to prevent the car from going out of the circle. Okay, so that's why the friction is towards the center of circle. All right, then the centripetal acceleration, just like chapter 4, we have all the forces, and we also draw the acceleration, isn't it? Acceleration. So this chapter 6 is the same as the chapter 4 forces. We also draw acceleration. But our acceleration is called the centripetal acceleration. Okay? So it has the resultant force. It has a resultant force because it has acceleration. Right? So our accelerations is the centripetal acceleration, and centripetal acceleration always towards the center of circle. Okay, so our center of circle is at the left hand side, so our centripetal accelerations is towards to the left. Okay, we need to draw the acceleration because we need to put the positive or negative sign, because we know that if follow acceleration we put positive, if opposite acceleration we put negative. Okay, so similarly we do the x and y components. Okay, for x component, the horizontal component, we have centripetal acceleration, so it has resultant force. So total Fx equal to ma, but this time our a has ac, called the centripetal acceleration. So it has, x component has resultant force, and do you know that this resultant force actually is the centripetal force? Okay, mac equal to fc, or total Fx equal to fc. Our y component has no acceleration, so total Fy equal to 0. That's it. Okay, now let's build equations based on x and y component. So in x component, what force do we have? We only have the static friction. Okay, And what is the sign? Follow acceleration. If follow acceleration is positive, opposite acceleration is negative. So our friction is positive. Our friction is positive because follow acceleration, same direction as acceleration. So static friction is positive. Now equal to MAC. Now we have the formula for AC. The formula for AC is V squared over R. Okay, V squared over R. And we already have the and so the centripetal force is also equal to mv squared over R. That's the formula. And we already have all the information needed. Just substitute inside. The mass is 1000 kilogram. Velocity is 15. And then radius is 50 meter, all in SI unit. So let's calculate what answer we get. We got 4,500 Newton. Okay. So what does it mean by this value? This value means 4,500 Newton means this is the friction needed when the car traveling at 50 meters speed. That means when the car traveling at this speed, velocity equal to 15, yeah, velocity equal to 15, the friction, the static friction needed for the car to turn safely is at least must be 4,500 Newton. Okay, this is the friction needed for this speed, 15 meter per second. So let's write that down. That is the friction needed. That is the friction needed, required for the car to turn. Maybe I just type there. Okay, the friction needed for car to turn safely, to turn the curve safely. Right, make it bigger. Yeah. So this is the friction needed for the car to turn safely. And now, also do the Y components. So the Y component, what do we have? We have the normal force. Normal force going upward, we put that as positive. The weight downward, negative. So N minus W equal to 0. So N equal to mg. That's it. Okay, N equal to mg. We got the normal force. Now, let's see the dry road. Yeah, let's see the dry road. The dry road has coefficient of static friction mu s equal to 0.6. 0.6. Okay. Now, for this dry road, let us find out how much maximum static friction it can provide. Okay. What is the limiting static friction it can provide? Yeah. Let's see. Let's calculate. To calculate the limiting static friction, limiting means the maximum. The maximum static friction that the dry road can provide for the car to turn safely. The limiting static friction formula is mu Sn. Okay, so we have mu s 0.6. The normal force we get from the Y component we calculate just now, N equal to mg. Put inside. Okay, let's put inside. So mu s is 0.6. And then this is mg. What is the mass? What is the mass? Mass is 1,000 kilogram, and then multiply 9.81, the G value. So we got 5,886 Newton. Okay. That means this is the maximum friction the road can provide. So that means, is it enough for the friction required? Yes, more than enough. The friction required to turn safely is only 4,500. But the road can provide 5,886 Newton. So it is more than enough. Okay, so we can say this we can say the limiting static friction is more than the friction needed, which is 5886 Newton is more than enough, more than the friction required for car to turn safely. So we can say, just type there, the road provides enough friction so the car can turn safely. Okay, make it bigger. All right, so I'll make it bigger now. Come on. Yeah. Okay, provide enough friction, the car can turn safely because more than 4,500. Now, how about the wet road? Let's calculate the limiting static friction the road provides. So, the mu s is only 0.3. The normal force is mg just now. Again, the mass only 1,000. Okay, 1,000 kilogram. So after we calculate, we got 2943 Newton. So the maximum friction the road can provide is only 2,943. Is it enough? No, the friction required is 4,500. But your limiting is only 2,900, so not enough. So the car cannot turn safely, it will skid. So what you can write is, you can write there, the limiting static friction, right? The limiting static friction is less than the friction needed. That means 2,943 Newton less than the friction required, 4,500 Newton. So less than, so the road not provide enough friction. So not provide enough friction, so the car cannot turn safely. Will skid, will slide across the road. Okay, so let's make the word bigger. All right, yeah, so that's a conclusion. Okay, so to know whether can turn or cannot turn, you just check the limiting static friction. So if the limiting static friction is more than the friction required, so has enough friction, can turn safely. But if the limiting, like the wet road, the limiting static friction is so small, lesser than the friction required, so not enough friction, the car cannot turn safely and will skid. Alright? So remember to draw the free body diagram for all things to work. Alright? Thank you very much. See you. Bye.